A century ago, Albert Einstein revolutionized our understanding of space, time, energy, and matter. We are still finding exciting confirmations of his predictions, like the gravitational waves observed last year by the LIGO experiment. When I think of the theme of today's event, ingenuity, Einstein springs to mind. Where did his ingenious ideas come from? A blend of qualities, perhaps, intuition, originality, brilliance. Einstein had the ability to look beyond the surface, to reveal the underlying structure. He was undaunted by common sense, the idea that things must be the way they seemed. He had the courage to pursue ideas that seemed absurd to others, and this set him free to be ingenious. A genius of his time, and every other. A key element for Einstein was imagination. Many of his discoveries came from his ability to reimagine the universe through thought experiments. At the age of 16, when he visualized riding on a beam of light, he realized that from this vantage, light would appear as a frozen wave. That image ultimately led to the theory of special relativity. 100 years later, physicists know far more about the universe than Einstein did. Now we have greater tools for discovery, such as particle accelerators, supercomputers, space telescopes, and experiments such as LIGO. Yet imagination remains our most powerful attribute. With it, we can roam anywhere in space and time. We can witness nature's most exotic phenomena, while driving in a car, snoozing in bed, or pretending to listen to someone boring at a party. Much of my own life has been spent exploring the nature of black holes, their geometry, evolution, and the fate of those unlucky enough to fall in. These greedy monsters are not easy travel destinations, but they fascinate me, and I keep going back. This year, Andy Strominger, Malcolm Perry, and I have reimagined black holes, examining the energy states of their vacuums, and the information stored on their boundaries, with potentially deep implications for physics. So if our minds, helped by data from telescopes and experiments, can cross the universe, making discoveries along the way, why go anywhere for real? Shouldn't we be content to be cosmic couch potatoes, enjoying the universe from the comfort of our home planet? No, we should not. The universe is a violent place. Stars engulf planets. Supernovas fire lethal rays across space. Asteroids hurtle around at hundreds of miles a second. Granted, these phenomena do not make space sound very inviting. Yet these are reasons why we should venture out into space instead of staying put. Because if we wait long enough, they will reach us here. I am not doomsaying. It is guaranteed by the laws of physics and probability. Furthermore, we know there is at least one advanced civilization with a propensity for destroying species, ecosystems, atmospheres, and weather patterns, perhaps entire planets. And it happens to live on Earth. Spreading out may be the only thing that saves us from ourselves. The second reason is that we are, by nature, explorers. The same curiosity that sends us to the stars, at the speed of thought, urges us to go there in reality. And whenever we make a great new leap, like the moon landings, we elevate humanity, bring people and nations together, usher in new discoveries, and new technologies. So far, such journeys have been limited to our local cosmic neighborhood. 40 years on, our most intrepid explorer, Voyager, has just made it to interstellar space. But that is still a very long way from reaching the stars. At Voyager speed, 11 miles a second, it would take about 70,000 years to reach our nearest star system, Alpha Centauri. It is 4.37 light years away, 25 trillion miles. If beings on Alpha Centauri are receiving television transmissions from Earth, they are still blissfully ignorant of the rise of Donald Trump. In fact, the distance to Alpha Centauri is so great that to reach it in a human lifetime, a spacecraft would have to carry fuel with roughly the mass of all the stars in the galaxy. In other words, with current technology, interstellar travel is utterly impractical. But we have a chance to change that, thanks to imagination and ingenuity. Last month I joined Yuri Milner to launch Breakthrough Starshot, a long-term research and development program aimed at making interstellar travel a reality. If we succeed, we will send a probe to Alpha Centauri within the lifetime of some of you watching today. Breakthrough Starshot brings together three concepts: miniaturized spacecraft, light propulsion, and phase-locked lasers. A starship, a fully functional space probe reduced to a few centimeters in size and grams in mass, will be attached to a light sail. Made from metamaterials, the light sail weighs no more than a few grams. The starship and light sail, together known as a nanocraft, will be placed in orbit. Meanwhile, on the ground, an array of lasers at the kilometer scale will combine into a single very powerful light beam. The beam is fired through the atmosphere, striking the sail in space with tens of gigawatts of power. The idea is that the nanocraft rides, like Einstein, on the light beam. Not quite to the speed of light, but to a fifth of it, or 100 million miles an hour. Such a system could reach Mars in an hour, reach Pluto in days, pass Voyager in under a week, and reach Alpha Centauri in just over 20 years. Once there, it could image any planets discovered in the system, test for magnetic fields and organic molecules, and send the data back to Earth in another laser beam. This tiny signal would be received by the same array of dishes that was used to transmit the launch beam. This would not be human interstellar travel. Even if it could be scaled up to a crewed vessel, it would be unable to stop. But it would be the moment when human culture goes interstellar, when we finally reach out into the galaxy. And if it should send back images of a habitable planet orbiting our closest neighbor, it could be of immense importance to the destiny of our civilization. Of course, there are major challenges to overcome. How to combine hundreds of lasers through the motion of the atmosphere. How to propel the sail without incinerating it, and aim it in precisely the right direction. How to keep the starship functioning for 20 years in the frozen void, and send a signal back across 4 light years with tiny lasers. But these are not limitations set by the laws of physics. They are engineering problems. The word engineer comes from the same root as the word ingenuity. Engineering challenges tend, eventually, to be solved. As it progresses to a mature technology, other highly exciting missions are envisaged. Even with less powerful laser arrays, journey times to other planets, the outer solar system, or interstellar space, could be vastly reduced. If we find a planet in the Alpha Centauri system, its image, captured by a camera traveling at a fifth of light speed, will be slightly distorted, due to the effects of special relativity. It would be the first time a spacecraft has flown fast enough to see such effects. In fact, Einstein's theory is central to the whole mission. Without it, we would have neither lasers, nor the ability to perform the calculations necessary for guidance, imaging, and data transmission over 25 trillion miles, at a fifth of light speed. So there is a direct path between that 16-year-old boy, dreaming of riding on a light beam, and our dream, which we hope will become a reality, of riding a light beam to the stars.
So in this lecture, I will try to convey the rationale behind a very ambitious project called the Breakthrough Starshot. And it all started on May 15th last year, when two people came out of a black car. One of them was Yuri Milner. The second is, who is a very visionary entrepreneur from Palo Alto, Silicon Valley. And the second is Pete Worden, who used to be 2 months earlier the director of NASA Ames, and stepped down because of these breakthrough initiatives that one of which I will describe. And they came to my office to ask if I'm willing to participate in those initiatives. And of course, I didn't think very long. I said yes. I gave them a tour of the Great Refractor, as you can see here. One of the initiatives was the possibility of visiting the nearest star to the sun. And the question was, is that feasible? And if so, what is the technology that is needed? And should we pursue it? It was not at all clear. And so the next step was to collect a group of postdocs and students that work with me towards other projects in astrophysics. And these are the names of the postdocs and students that were sort of advisors, an advisory group that we basically used to go through various ideas. So some people came to visit us and propose various techniques that could be used to visit the nearest star. And the challenge is, of course, that the nearest star is about 4 light years away. And if we want to visit it within our lifetime, and obviously any project that lasts much longer than a human's lifetime has much less enthusiasm around it, right? Projects that last centuries will not get funded very easily. So the idea is to visit the nearest star within our lifetime, within our generation. And to do so, you need to move the spacecraft at a fraction of the speed of light. At least a fifth of the speed of light, so that it will take no more than 20 years. And so there aren't many technologies, as I'll describe, that can do that. And so we bounced ideas, and then at the end of December, I usually go back to visit Israel for a week or two. And my wife said, let's go to a goat farm for the weekend. It's a very pristine, nice environment. And since I grew up in a farm, as Charles mentioned, I sort of like to be away from people and be closer to nature. So I said, great, let's do it. And the morning we were heading that way, I got a phone call from Pete Worden saying, Yuri Milner would like you to describe the conclusions of your deliberations within your group and tell us whether you find anything interesting. And I said, okay, I'll prepare the talk. And he wanted me to deliver the talk 2 weeks later, so I had to prepare it while being in the goat farm. I got to the goat farm, there wasn't any internet connectivity. And so the only place was in the near the reception, the office, they called it, which was a sort of a cabin. And I sat at 6 a.m. in the morning with my back to the wall, working on this laptop, making up a presentation, recommending the most feasible technique that I think might be useful. And it was really a surrealistic view to look at the young goats that were born just a day before and contemplate a trip to the nearest star. I don't think the owner of the goat farm ever thought that this would happen in his goat farm. And then we had many deliberations, many discussions. I made a presentation and described the technology that I'll talk about today. And the end result, after many, many long hours of discussions with Yuri Milner, Pete Warden, and Pete Klupar at the Breakthrough Prize Foundation, we came out with a public announcement on Yuri's Night, which is celebrating Yuri Gagarin's visit to space, the first human to go to space. On the 12th of April this year, at the One World Observatory in New York City, on Earth, we described this project that we would like to initiate. And Yuri described it. This is Yuri Milner. You can see here Freeman Dyson. And Stephen Hawking came to this public announcement and participated in it. The board of this project includes 3 people, Yuri Milner, Mark Zuckerberg, and Stephen Hawking. Currently it's funded at a level of $100 million for the next 5 to 10 years with the objective of eventually, if it looks promising, increasing the scale of funding by 2 orders of magnitude. So it will become a project at the level of CERN or JWST once we get to the full system, if the technology seems promising. And this is a photo from April 15th, just a few days after the public announcement. There was a conference in Palo Alto, and these are some of my students and postdocs that came there. And they are in the audience. And we took the opportunity of Stephen visiting here to also inaugurate the Black Hole Initiative, which is the only center worldwide that studies black holes. And that's a collaboration between physics, astronomy, philosophy, and math. And you can see some of the PIs here in this picture. My daughter was very fascinated by Stephen Hawking. She even she studied his life and was very impressed by his optimism. She gave a lecture at her class about him. And he was, I think he enjoyed very much the visit. One of the nights, we went to many dinners, and after one of them, he said to the people that take care of him, let's go to the bar at the Charles Hotel. So he really had fun around here. He came to our house. This is our house for Passover, actually. So we announced the project. What is the project about? There were a bunch of commentators at the public announcement. The Kepler satellite informed us that about a quarter, or perhaps a little more than that, of all the stars in the Milky Way host a habitable Earth. What you're seeing in this plot is the flux from the star in units of the flux on Earth as a function of the temperature on the surface of the star. The sun is pretty close, 5,700 or so. And there are planets with a mass comparable to the Earth around stars like the sun or smaller. The nearest stars around us are depicted here. And the very nearest one is Proxima, which is the 3rd member of a system called Alpha Centauri, A and B. So there are 2 stars there. And here's another picture. This is the Oort cloud around the sun, 2 light years away, and then 4 light years away. Just beyond that is where the triple system of Alpha Centauri is, Alpha Cen A and B and Proxima. These are the 2 stars. You can see them, quite bright. They're separated apart quite widely on the sky, just because they are close to us. And here is Proxima here. It's about 12% of the mass of the sun. The 2 stars are very close to the mass of the sun. But Proxima is a dwarf star, and its lifetime is trillions of years. So actually, if you wait for the future, stars like Proxima will be the most abundant stars. And it's really an urgent and important question to ask whether life is possible around low-mass stars, because these would be the stars that will populate our galaxy in the distant future, trillions of years from now. And if life is possible next to them, that will be the most common form of life. In fact, life is most likely to exist in the universe, in the future, trillions of years from now, around low-mass stars. These are the most abundant stars that are 10 times more abundant than solar-type stars. So it's quite surprising that we are located close to the sun when such stars are more abundant and they will live for much longer. But we can correct that by moving there. And I already urged some friends to buy real estate on the planet near Proxima because the price will only go up with time. Now, there was a planet found called Proxima b. It was announced this summer, just a few months ago. And since this star is only 12% of the mass of the sun, it's very faint. And so the habitable zone, the zone where a planet needs to be so that liquid water would exist on its surface, so that the surface temperature would be similar to Earth's, that distance is 20 times closer than the Earth-Sun distance. And so it takes 11.2 days for that planet to move around Proxima. That means that if there is life, if there are people there, they celebrate birthdays every 11.2 days. They also need infrared eyes because the star is 2 times cooler than the sun. And obviously, the key question is whether there is an atmosphere around that planet, because liquid water could exist only if there is external pressure, atmospheric pressure. And that's why you need a planet with a mass comparable to that of the Earth, because if you consider objects much smaller than the Earth, they cannot retain their atmosphere, the atmosphere evaporates, and then they cannot have liquid water, so we cannot have life as we know it. So the key question here is whether an atmosphere exists or whether it was stripped perhaps by flares from this host star. And one way to find that out is with the James Webb Space Telescope. This is a paper we wrote with Laura Kreitberg, who is a Harvard Junior Fellow here, where we argued that just measuring the temperature contrast between the day side and the night side of this planet could tell you whether it has an atmosphere. Without an atmosphere, there would be a very large contrast between the day and night side. The planet is locked. It always faces the star on the same side, so one side of it is very warm and the other side is freezing cold. The real estate value will be highest in between those. You're sort of either in a permanent summer or permanent winter on this planet. But the temperature contrast would be moderated if there is an atmosphere circulation, or if there is an ocean that distributes heat from the hot side to the cold side. And so JWST could in principle measure the temperature contrast between the two sides by monitoring several orbits of this planet around Proxima, because just like the moon, you would see phases of the planet with varying areas as the planet moves around the star. And so as a function of time, you can tell what the temperature contrast is between the day and night side. And with pretty good error bars, JWST could tell us within a couple of years whether the planet has an atmosphere. Now, can we visit the stars? Can we visit Proxima now that we know that there is a habitable planet around it, Proxima b? Can we go there with a camera and take photographs of the surface of this planet, just like New Horizons took photographs of Pluto? The motivations for visiting nearby stars are many. We might, in the long term, wish to find alternatives to Earth. We want to extend the longevity of our civilization, and there are many risks to staying on Earth, putting aside politics. There are issues to do with, of course, asteroid impacts that presumably killed the dinosaurs, global climate change, and potentially wars, biological or nuclear weapons use. There is also the much more noble motivation of exploring our galaxy, discovering whether there is life elsewhere, as I mentioned, taking photographs. The sun can be used as a gravitational lens if you just position yourself far enough from it. And then you can get very high resolution of background objects. In principle, one can imagine tourism or establishing colonies, visiting extreme environments, and so forth. And ultimately, we can, in principle, plant 3D printers in various places that will produce whatever we want in those locations from the raw materials that are available. We don't need to send humans there. We can just send human DNA, the information of how to make a biological entity, and then these printers will make them over there. So if you think about the speed as a function of time in human history, of course, early on we just walked or ran, and then Ford invented this T car, and then within 50 years, airplanes and eventually Sputnik brought us 1,000 times faster. So over 50 years, a jump in 3 orders of magnitude in speed, and since Sputnik was launched, we are getting to the point where it's 50 years ago. And it's about time to get another advance of a factor of 1,000. It so happens that the New Horizons moved roughly at the speed of Sputnik. I mean, most of the spacecrafts that were launched moved at of order 15 to 20 kilometers per second. And as I'll explain the physics of that in a minute. So we definitely need a new technology in order to achieve higher speeds. Some basic numbers to keep in mind. If we accelerate an object at 1g, meaning the acceleration that we feel here on Earth, on the surface of the Earth, if you accelerate it at 1g for 1 year, you get to the speed of light. It's a useful number to remember. If you are sitting on a spacecraft that moves at 1g, you cannot tell the difference between gravity and the spacecraft pushing you at 1g. It's a very convenient environment. We would feel just like at home. But within a year, we would reach the speed of light. And if you continue to do that, then at a steady 1g acceleration, in principle, you can cross the entire universe because the Lorentz factor grows exponentially. With proper time. So within a couple of decades, within 25 years, we can cross gigaparsecs. If we only had a vehicle that can accelerate us at 1g, we would feel very comfortable on it, just like the Earth. For 25 years, we would reach gigaparsecs away. That's quite remarkable. Now, what is limiting us? Why are we stuck here? Well, basically, it's the energy per unit mass that any fuel can provide. So the energy per unit mass gives you the maximum kinetic energy that is available. Or if you, the maximum velocity squared over 2. Now, if you consider chemical propellants, this velocity, maximum velocity that you get is of order 1, maybe 2 kilometers per second. That's why rifles or guns can accelerate bullets only to a speed of the order of 1 or 2 kilometers per second, not more than that. What happens is if you try to accelerate a bullet, even if you build a very long barrel, it doesn't matter. Once the bullet reaches that speed, the gas behind it gets rarefied. There is a rarefaction wave, and the gas cannot catch up because the bullet moves faster than the sound speed. So you end up with a maximum speed that is comparable to the sound speed. Then with nuclear fuel, radioactive fuel, you can reach maybe 1,000 times more because you get 1 to 10 MeV per proton. So that a proton is a GeV, so that ends up giving you a maximum speed of order 1,000 kilometers per second. Perhaps more than that. This is with radioactivity, if you have just radioactive elements. If you have fission, you can get up to 10 to the 4 kilometers per second. And with fusion, you can get to 1/10 of the speed of light if you use all this energy. And if you have an external source, if you don't carry the fuel with the spacecraft, in principle, you can reach the speed of light. There is nothing to prevent that from happening. So in terms of the momentum, the best way to achieve the speed of light is reflecting light. So if you imagine a mirror reflecting light, the amount of momentum given to the mirror is, since you get twice the momentum of the photon, since it bounces exactly in the opposite direction, you get twice the energy over the speed of light as the amount of momentum kick out of this deposition of energy. If you instead deposit the energy in matter and release matter from an exhaust, then you can get more than that, because the energy is the momentum squared over twice the mass of the fuel. And you can write this as momentum times speed divided by 2. And then the change in the momentum is, again, twice the energy over the speed of light. But this time there is an extra factor of the speed of light over the speed of the gas at the exhaust. So in fact, the momentum that you get per unit energy is much more in case you are ejecting matter. But if you want to reach the speed of light, it really doesn't matter. You really want to use light. It's sort of obvious. There is this equation, momentum equation, which tells you that the force acting on the spacecraft is given by the mass loss. If you have just matter leaving the exhaust, the mass loss per unit time, the mass loss rate, times the speed of the gas at the exhaust relative to the spacecraft, which is roughly the sound speed. So if you try to solve this equation, it's very easy. You have m here, dm dt on this side. You end up with the very well-known solution to the rocket equation, which tells you that the rocket speed, the terminal speed, is the exhaust speed times the logarithm of the initial mass of this rocket divided by its final mass. And that's the tyranny of the rocket equation. You have this logarithm here. So at best, you can hope to put several orders of magnitude in this parenthesis, but that will buy you at most a factor of 10 in terms of the speed of the rocket. And that's why all the spacecrafts that were launched into space using rocketry, the conventional propellants, they reach only 15, 20, maybe several tens of kilometers per second, but not more than that, because you really need to put a huge amount of fuel on top of a tiny amount of mass in order to get a little more than that. And it grows only logarithmically. So the key is to increase this exhaust speed. And the most conservative approach would be to use radioactive fuel, where you use, for example, New Horizons use 11 kilograms of plutonium. It was a fair fraction of the plutonium available, actually, because of the ban on producing plutonium. But that buys you only 1,000 kilometers per second. And if you want to reach the speed of light, or a fraction of it, you better use light. There is also the possibility of using fusion, but I put that as a more risky proposition. So we actually evaluated proposals that were submitted to us, to my group, and it doesn't seem like it's feasible in the near future. The motto about fusion is that it's always 10 years into the future. So we all know about sails and the way of using wind to propel a sailboat. Can we extend that concept to go to the stars? And in fact, this is not a new idea. Kepler wrote a letter to Galileo in 1610, in which he said, "With ships or sails built for heavenly breezes, some will venture into that great vastness." So he already thought about it. So we should always reference that, 1610. Nothing is new. Shortly after lasers were invented, in 1962, Robert Forward wrote a paper suggesting using lasers to propel spacecrafts. Basically, to push a sail with laser light. This appears to be a very efficient method if you're aiming to get to very high speeds. And there were a bunch of papers a few years later in Nature, also in Physical Review letters and so forth. And the idea was to use a very powerful laser and push on a sail. And I will not get into the details, we'll get to them a bit later. Of course, if other civilizations are more advanced than we are, they're already doing that. And so with James Gwilshon, who is a postdoc here, we studied the possibility of detecting beacons of light that may be associated with other civilizations, trying to push a sail and bring cargoes, let's say, from Earth to Mars. If you have a planetary system similar to ours, you might think that we would at some point colonize Mars, and there would be industrial interest in transferring goods between the two. And if you do it with light pushing sails, actually you can optimize the frequency that is needed of the radiation that is needed for such a journey. If you want to move the cargo at 1G so that it doesn't get ripped apart, then it turns out that microwaves are a very good frequency regime, 60 gigahertz or so. And it's impossible to avoid leakage of the radiation outside the sail. So the sail never perfectly blocks the light. And so an observer far away could, in principle, see these beacons of light. How would they look like? Well, we figured out that they would typically last, if you imagine a system like the Earth and Mars, they would last for a few seconds, and they will be at a distance of 100 parsecs, they will be roughly a millijansky. That's what's necessary to lift about a ton of cargo between Earth and Mars. So perhaps, you know, they're not very different than fast radio bursts, but they are different because there is no necessarily dispersion measure associated with these pulses. But it's interesting to contemplate the possibility that we might detect one day these beams of light passing through. So if you work out the math, it's really straightforward. I mean, it's just very simple equations. You end up with this relation that the speed that the spacecraft achieves scales like the square root of the power that you're using times the size of the array that is making the laser beam divided by the wavelength, so that it goes like to the power of 1/2, and then the mass to the -1/4. And this is assuming that the thickness of the sail is fixed, because usually you want to minimize the weight of the sail. So it needs to be of the order of the wavelength of the radiation that one is using. And to reach very high speeds, you actually need to use very short wavelength radiation. That's much more optimal. So 1 micron, let's say. And so you can imagine a thickness of the sail being roughly a micron or a fraction of a micron. And there is rather weak dependence on the mass in that regime. If I use this laser pointer to accelerate a single gram, so if I shine it at a gram in space without gravity, then it will reach the speed of an ant, roughly a few millimeters per second over a week. Okay, that's the scale. How can we achieve the speed of light? Well, we can shine it for a Hubble time, but a better approach is actually to use a much more powerful laser, 50 gigawatt, and then over a time of a couple of minutes, and an energy of order 10 terajoules. These numbers are comparable to what's needed to lift off the space shuttle. You roughly need 50 gigawatt, a few minutes, 10 terajoules. That's what's used for the space shuttle. With that much power and time, you reach a fifth of the speed of light with 1 gram. Okay? And the sail could be 4 meters on a side, and it matches the size of the spot of the laser at the diffraction limit across the acceleration distance of 2 million kilometers. So this spacecraft will go 2 million kilometers because it moves at the end at 0.2 c, in the middle of its journey, 0.1 c. So over a couple of minutes, it reaches a distance that is 5-6 times larger than the moon distance. And the diffraction limit at 1 micron is roughly a couple of meters. For a square array of laser beams that are combined to a single beam that occupies roughly a square kilometer. So you imagine an array of small lasers combining coherently to make a single laser beam, and they span a kilometer square, diffraction limited. You end up with a few meters spot at a distance of 2 million kilometers. That's what's needed to reach a fifth of the speed of light. 1 gram. It's a huge effort. The acceleration is roughly 60,000 G. How can we achieve that? Well, there are 3 technologies that come together, actually for the first time in human history, this decade. One is the miniaturization of electronics. If you look at your iPhone and you strip it from the protecting case and from the human interface, you end up with electronics that weighs less than a gram. And this is already here. So we can have a camera, navigation, communication, all of this packed within a single gram. There is the nanotechnology of material science. In principle, there are materials that can be very thin and light that could serve as the sail. And there is the revolution of lasers, the fact that we can combine multiple laser beams coherently. So let me start with the electronics. This is an example for a chip. This is an Apple Watch chip. I actually have it right here. And I love this watch. This would be sort of the expected size of a star chip. In fact, you can put it on the sail itself. It doesn't need to be separate in principle. And it can have components like a camera, a magnetometer if you want to measure magnetic fields. It really depends on which probes you want to put on this. There would definitely be enough room for many cameras, not just one, similar to the cameras that you have on an iPhone. There would be a communications laser that will transmit the image that is taken by the cameras. And then a battery that includes radioactive material. So that's an example. And if you sum up the weight of all these components, you end up with less than a gram today. So this is definitely doable if we imagine a project that will take several decades for completion. So in fact, one can get to a fifth of a gram with existing technology. Now the sail is a big challenge because the material needs to be sturdy, very strong. It's being illuminated by the laser, but it will not be uniformly illuminated, so it needs to sustain force differences or shear, but it also needs to avoid absorbing more than 10 to the minus 5 of the laser energy, because the laser is very powerful. We're talking about 50 gigawatt, 100 gigawatt. If only 10 minus 5 of that power is getting absorbed, it will burn the sail, sort of like Icarus wings burning at the sun. So you need a very small absorptivity, and one way to achieve it is with a very high reflectivity. And there are materials being designed these days that can achieve that, but they were not demonstrated yet. So that's another challenge. Lasers is another technology that is getting better and better. And you can see here Moore's law for lasers. That's the power that CW lasers have as a function of the year. And the doubling time is about 1.7 years, or 20 months. So the laser power is rising exponentially. Laser costs are falling exponentially. And we really need these exponential laws so that the project will be affordable, so that it will be less than $10 billion, let's say 20 years from now. The idea is to combine multiple laser beams, each of which is low power, into a single extremely powerful beam. And for that, you need phase locking. You need to correct for any phase errors in each of the laser beams that you are combining. Otherwise, you will not achieve the diffraction limit. The spot would be very big. A lot of the energy will be wasted. It will not fall on the sail. Material strength of the sail is a big issue, and low absorptivity. It could be a rather thin layer, and we know that graphene, for example, is a very strong material that in principle could be used. And then the concept is that one is shining the laser beam on this sail in an attempt to reach 20% of the speed of light, reach the Alpha Centauri system within 20 years, and send back images. And the most important thing is that during the acceleration, you want the sail to stay on the beam. So there is an issue of stability. The question is, if you perturb the sail slightly sideways or in any other way, would it continue to ride on the beam, or would it slide to the side? And actually, the first detailed paper that was dedicated to this problem was written by Zach Manchester, a postdoc in the engineering department here at Harvard, that we are finishing these days. And we found that, in fact, one stable configuration that looks most attractive is actually that of a ping pong ball, basically a spherical shell that appears to be very stable to a hollow beam, laser beam. So you can, in principle, shape the beam and shape the sail in a way that would keep them stable. A parachute configuration is not necessarily stable, actually. And then we want to put the chip on top of the sail. In principle, you might think, oh, maybe we can use sunlight, which is many different wavelengths. The problem there is that the power, the flux of the sun is not large enough. You need to construct a huge sail in order to capture enough momentum. So, but that was used by the Icarus probe. It used a 20-meter sail driven by the sun, but the speed was rather small. In principle, one can tap also the solar wind. That gets you at most to kilometer per second, 800 kilometers per second or so. So what are the components of this of the system? We have to at first obviously construct the nanocraft, this spacecraft, made of the ingredients that I mentioned. There is a need to construct the laser beamer. So that's a combination of many small laser beams that combine together to make the powerful coherent beam. Eventually, we hope within 2-3 decades, we can get to the point of launching something. The launch itself takes minutes, a couple of minutes. For each spacecraft, one can launch many of them. So this technology allows you to, in principle, launch as many systems as you want because they're relatively cheap. Once you have the infrastructure, you can launch one sail per day. And so there could be hundreds or thousands of them launched in different directions to explore different things. If you're interested in Planet 9 and what's going on it, you can shoot such a thing. It would reach Pluto within a few days. So in difference from New Horizons that took 9.5 years, moving at 0.2 C allows you to explore Pluto on the same week. The NASA administrator had to change during the mission lifetime of New Horizons. So it's a big difference. If you can launch small nanocrafts, many of them at a relatively low cost, once you have the infrastructure, that makes a completely different strategy to exploring space. And then, of course, there is a very long time of cruising towards the target. So in the case of the Alpha Centauri system, it will take 20 years at 0.2 C, a couple of decades where, things will be rather boring. So 2 minutes for the launch and then a couple of decades waiting for it to reach it. And then the encounter. So passing close to a planet there would take hours. And then there is the data delivery. And for that, the earliest that we can hope for is 4.24 years, the time it takes light to reach us from the Proxima system. So the steps are many, and of course, in principle, one can fabricate light cells once we know which material to use, what shape to give it, how to produce it, then we can make many of these. And obviously, within a couple of decades, making such things would become much cheaper. We're aiming to have a diameter of order 4 meters and a gram scale weight. And then combining, this is just an artist illustration. It's by no means meant to represent individual lasers the way they should look like. But the idea is to use fibers and correct for phase errors and combine multiple laser beams into a single coherent beam over an array that has a size of the order of 1 kilometer. These are existing solar thermal arrays, what you're seeing here. Now, which wavelength to use depends on the atmosphere. If you build this array on the Earth, and at first we contemplated the possibility of space, but that makes it much more expensive. And also you would need to construct such a structure in space with robots. It would be so huge and so expensive. There is no way to do it at the same price tag. So it's much more practical to build the laser array on the ground. Then you have to cope with passing it through the atmosphere. And for that purpose, there are some windows where the atmosphere doesn't do much to the laser or does less, that transmits it, doesn't absorb it. And around a micron is a good regime to work in. There is obviously the turbulence in the atmosphere, but one can correct for the phase errors using adaptive optics. One can put a beacon on the spacecraft or on the way to the spacecraft that will inform in real time about turbulence in the atmosphere. And just like we use adaptive optics nowadays, in principle, with a much more sophisticated system, obviously we're talking about an active target, a target that is cooperative with us. We can plan things on the target in difference from targets that the military aims at, which are trying to avoid the laser. Here we have a cooperative target that can in principle allow us to phase correct and aim at it. And there are a variety of possible locations for putting such an array, one of which is in Chile, in the Atacama Desert, another one in Australia. We haven't yet, obviously, converged with the location. And in terms of the power generation, the idea is to use existing infrastructure, build, potentially, another option is to build a power plant near the launch site. But that power can come, for example, from the sun. So if you think about it conceptually, the sun delivers roughly 1 kilowatt per square meter. So if you have 1 kilometer squared array of solar cells, you will end up getting 100 gigawatt out of that, because you have kilowatt per square meter, and there are 1 million square meter. Sorry, you will get a gigawatt from that, but a gigawatt just from the sun, if you make it 10 kilometers, then you will get 100 gigawatt. And that's enough power in real time to provide the launch. In principle, you can store that power. You can have just 1 gigawatt from the sun, store it for a while, and then release it over a couple of minutes. So in terms of storage, one can use batteries or capacitors or flywheels. Again, we haven't converged with a specific element. In terms of the launch, the idea is to have a mothership that brings, that is brought into space with a rocket. And the mothership has a lot of small spacecrafts with their sails in it. So it's like a mother having a lot of babies in its belly. So that's the way to think of it. And it has an orbit such that it will release those spacecrafts at the right time, at the right place. So here is the deployment of a nanocraft from, I mean, just conceptually. We haven't yet designed it, of course. And then the launch will be of roughly 1 gram that will be accelerated over a couple of minutes. The launch will begin at around 60,000 kilometers from Earth. And the ultimate speed is a fifth of the speed of light, 60,000 kilometers per second. And you can imagine once a day such a launch. It's very cheap. I mean, the cost of such a sail would be of the order of hundreds of dollars. It would be really cheap because the materials are relatively cheap. If you think about an iPhone, it costs a few $100s. And so the real investment in funding is actually to build the infrastructure, not to produce the spacecrafts. There is, of course, a policy issue. Of course, we don't want to hit any of these existing satellites out there with a laser beam. There would be issues to do with other countries worried about aiming at them. And that's another reason for putting the laser on the ground, because if you put it in space, people would worry that you can point it at them. Although, even in this case, one can put a mirror such that it will go to, and I'm sure North Korea, will be worried about that. And then the cruise of a couple of decades, where this spacecraft will move through space. Of course, you want to minimize the cross-sectional area of this spacecraft such that it will not bump into anything along the way. But it's a long time, a couple of decades. And some of these spacecraft will be lost. So that's another reason to send many of them. Interstellar dust is a concern. And we actually wrote a paper with Blakesley Burkhardt, who is in the audience, postdoc here, Tim Huang and Alex Lazarian, that we are just replying to the referee right now. In fact, I got an email the other week from Fred Rassio, the editor of the Astrophysical Journal Letters, who said that any paper written on Starshot should be sent to him. He's so intrigued by this concept that he would like to, for his referees to look at these concepts. And so in terms of this interstellar dust risk, if you imagine a dust grain, if you go to the rest frame of the spacecraft, the dust grain is moving relativistically at 0.2 c, the speed of light. So it's sort of like it releases an amount of energy per proton similar to a nuclear explosion. So think of it as a tiny atomic bomb hitting you. And it will create a crater with some melting around it. And so in this paper, we calculated the likelihood of that happening, which fraction of the volume of a spacecraft, let's say the thickness of the material is 0.1 millimeters. So if you imagine, for example, folding the sail to a needle-like configuration such that there is some protection to the electronics in front of it, with a thickness of 1/10 of a millimeter, what you see here in the gray region is the expected column density of hydrogen towards the Alpha Centauri system. So we don't know exactly the interstellar medium density, but we should have a column density somewhere between 3 times 10 to the 17 and 10 to the 18 per square centimeter. And in that range, a fraction of maybe 10 to 20% of the volume of this layer of 1/10 of a millimeter will be damaged. If you make it out of quartz, if you make it out of graphite, these are the numbers here. In terms of melting and erosion, this is the fraction of the surface that it's getting bombarded by. Now, there are two things that bombard it. One is dust grains, but there are also the protons, helium atoms, heavy elements, and so forth, and we included that. And the bottom line is that with appropriate design, you can, in principle, suppress the damage, and you can protect the electronics. Eventually, one would get to the encounter with a planet. And just think of it flying by a planet at 1/5 of the speed of light. Naively, you would think if you're moving relativistically next to a source, there would be Lorentz contraction. So the source, suppose the planet has a circular appearance when you're at rest relative to the planet, you would think that it would look ellipsoidal, squished. That's the wrong intuition. It turns out that special relativity, and that is based on a paper written about 50 years ago, special relativity implies that the image that you take with a camera, even if you move very close to the speed of light, the planet would still look circular. It will just appear rotated. And that's if you take into account the time delay associated with the photography. This was a paper by Terrell, and Penrose also wrote a paper about this. It's called the Terrell effect. But together with Pierre Christian, we actually consider the possibility of having an interferometer on the chip. And we asked the question, can you measure the time delay, and can you actually infer various parameters like the distance or the acceleration exerted on the spacecraft as it flies by? And the answer is yes. That's another paper that we submitted recently on this subject. And in principle, the idea is to take an image, a photo of the surface of the planet, see if there is life there. Is it green? Has vegetation? Is it blue? Does it have oceans? Are there people waving their hands? And then the data has to be delivered. It will take 4 years for us to get it. It will be very nerve-wracking if we live through that time. And the idea is that the lasers on board the chip will send the information back to Earth. It's easy to find the Earth because the Earth is near the sun. So you always look at the sun, and the Earth is just next to it. So you just transmit the information towards the sun. Each nanocraft will use a beamer, a laser that, the idea is that the beam from the nanocraft will intercept the Earth, and at this phase of the project, one would use the array that was used to launch the spacecraft now for receiving the signal. So again, a kilometer squared collecting area. There are many challenges. Needless to say, this is not an easy task, but it's the only feasible way to move forward. And as I told Ur Miller, so I actually gave that talk back in January at his home, and my conclusion was there aren't many possibilities. It's not as if we have a number of technologies that we can use for that purpose and select the best one. There is only one that seems feasible in principle that we can dream of using given the advances over the past decade in the 3 areas that I mentioned. And we are very lucky that there is one. It's sort of like getting married. You know, you are happy that there is one solution to this problem. You know, there could have been nothing. We could have ended up the discussion and said, no way, there is no point in thinking about this. But it's very challenging. And I mentioned some of the challenges. Of course, they involve making the sail. That's the biggest challenge, in my opinion, that is sufficient, that has integrity under the thrust of the laser, that rides in a stable way on the laser beam, that is sufficiently light. There is the challenge of making the laser array, combining these beams, correcting for the phase errors, making them a single coherent beam at the diffraction limit. There are policy issues. Some people tell me humans are much more difficult than any physical system. So dealing with other governments could be a major issue. And then there is the launch, the cruise, there are collisions with dust particles, and the communication, eventually getting the signal back to Earth. We do have an advisory committee of the project, and the members are listed here. Some of them are very distinguished. As you can see, we have a Nobel laureate. You can recognize some of the names. And the bottom line is that for the first time in human history, we can do more than just gaze at the stars. We can actually reach them. And this is just the beginning. Now is the time to begin the feasibility study of this technology, it will cost about $100 million over 5 to 10 years to figure out if the technology is feasible. And if it is, we hope there will be sufficiently wealthy individuals interested in supporting it, and perhaps some governments. So let me conclude with a brief video in which I summarize the concept. And there is no audio track here. So this is the mothership that releases a single spacecraft, a laser sail. Oops. Sorry. So here is a sail. For some reason, it stops. Let's see. Well, I guess we'll just give it another try. And when it gets to the right place at the right time, the laser points at it and pushes it. That's the concept. 2 million kilometers away, the acceleration stops. And here is another launch, let's say a day later. It's being pushed, and then the acceleration stops. In principle, the sail can point sideways to reduce the chance of intercepting dust particles, or you can imagine folding the sail into a needle-like configuration. Then it passes the Oort cloud. It could take some photographs along the way, and then it gets close to the star of interest, and next to a planet that here looks like the Earth. Doesn't need to be that way. And here are the photos. And these photos are eventually transmitted back through the small lasers on board the spacecraft. They pass through the solar system, and eventually this laser beam illuminates the Earth. And now the array is in the receiver mode, receives the signal. And this is the concept. Thank you.
Thank you. Well, I imagine there might be a question or two.
Many questions, but I'll restrict it to two. What is since this is a free flyer, how accurately, you're moving a great distance, and so if you want to fly by the planet and not catch it, at the other side of its orbit, how precisely does that happen?
So first thing to keep in mind is that stars move relative to each other. You're not pointing at the star, you're pointing at where the star will be in 20 years.
Right.
You have to know the proper motion very precisely. And also the binary motion. The 1 AU at 1 parsec is an arc second.
Right.
That's easy to remember. You need to be within an arc second if you want to be within 1 AU of the planet, because the planet would move around the star. It will be difficult to time the arrival to good enough precision so that you know the phase of. So if you want to be within 1 AU, let's say of alpha cen A or B, then you need an arc second precision. Now, even if you shoot it, so first of all, you can shoot a number of these, like spray the system, and then one of them will pass close. But you could also correct for through a navigation device by, for example, if you shine a laser from the sail, you can position various lasers across the sail such that they will give a little bit of thrust. And we went through the calculation. There is enough thrust in lasers to correct the direction within an arc second, such that you will arrive at the right place at the right time.
The other question is, just like with the reflectivity of the sail, I would think you have to worry about the very details of the transmission of the Earth's atmosphere around 1 micron, because you're pumping a huge amount of energy, and if it's not 100.000% transmissive, then you're heating the atmosphere.
That's right.
And over 2 minutes, I mean, I don't know, but you could conceivably, over 2 minutes, change the atmospheric transmission.
You could, and that will be a subject for future study. There would be a lot of studies that have to be done along the way. In principle, it would be ideal if there is sort of a hole drilled along the direction, because then you don't have the turbulence affecting the beam quality.
Just over there. Yes.
So I mean, so 0.2c is a nice round number, but presumably that's not the optimal. So why not 0.3? I don't know, how much did you think about it?
Well, so this question was brought up. We had a meeting of the advisory board, and the older member of the advisory board is Roald Sagdev, very distinguished plasma physicist. And Sagdev said, why do you stick with 0.2c? I mean, the speed should reflect the life expectancy of all members of the advisory board. So the 0.2c was selected because both Yuri and myself are 54 years old. So based on our life expectancy, we wanted the project to be completed during our lifetime. But in principle, you're right. I mean, it may well be better to aim at 0.8c so that, if you want more rapid satisfaction. But it obviously becomes more challenging in terms of the laser and the cost. But these are just fiducial numbers, getting there in a few decades so that we will still be there, and getting the cost to be reasonable within the cost of CERN, let's say.
But there's a large error bar still on
The real issue is whether Moore's law will continue to apply 20 years from now to laser technology, because that would be the most costly element. But this project, the importance of it is that the importance of the concept is that you invest mostly in infrastructure. So you're not investing in the launch, in each launch. And in that sense, it's a one-time investment. If our humanity wants to explore the stars by visiting them, as a first step towards gaining information about real estate nearby, then we definitely want to start with this. Now, it's also possible to go along a different route and say, okay, let's allow ourselves 80,000 years to get there with current rocket propellants. We can do that. But then we have to wait 80,000 years. I don't think many of us are patient, and I don't think the taxpayer will give, or any person would give money towards such a project, unless we increase our life expectancy. So another possible approach would be to ask biologists to extend our life expectancy to 1 million years, such that we can imagine projects that take less than 1 million years.
Or
So, two questions. One, what do we know about the activity of Proxima, and how would that affect if you have eruptions? And the second one, playing devil's advocate, since we're talking about something that might happen 40 years from now, wouldn't it be easier to construct a much larger telescope in space in order to resolve Proxima beats?
Yeah, these are excellent questions. So with respect to the activity of Proxima, there were actually observations by MOST reported recently, shortly after Proxima B was discovered. And the activity is not large right now. It's not clear that if there was an atmosphere to the planet, it would be lifted off as a result of heating by the flares. However, dwarf stars are known to flare a lot more when they're younger. So the issue is really whether the reason that we are next to a star like the Sun is because lower mass stars that are more abundant and longer lived, where we would have found much better environments for habitable Earths to be, whether these low mass stars are just too active early on, such that the flares strip planets out of their atmospheres, and that's why we don't find ourselves there, even though these are the more common. So that's a key question. I think that is the most interesting question in exoplanet, the search for life. Find out whether low mass planets allow habitable Earths to retain their atmospheres. And the first place where we should start is Proxima. There is another planet that was found recently close to a dwarf star in the habitable zone of that interest. So we can just explore the systems that we know about. Now, with respect to your second question, what you really need is, if you wanted to achieve the same resolution as a flyby, and by the way, you can ask the same question about exploring the solar system. You can ask, why send new horizons? Why not build a space telescope that will image Pluto from a distance? So there are two answers to that. First, it was not done, as you can tell, because it's much more expensive. It turns out that all the missions to image planets used flybys rather than a big telescope. And the other thing is that visiting a system is not the same as looking at it from a distance. You know, when I look at my backyard from the window of my house, I see one thing, but when I go and visit it, I see squirrels running around, I see rabbits and so forth. It's quite different, you know, when you're, and also it allows you, if you have that technology, it allows you to deliver things there. And I think it's an ambition that we should have, irrespective of the specific agenda we have in terms of the science. We should develop the technology to visit places, because it's a completely different thing than looking at them from a distance.
So I would just counter the last argument just as a bird watcher. Sometimes it's more important to monitor something over a long time than to visit it for a short time. You won't always see hawks and eagles if you visit a place just once.
Okay, we can do both. In principle, we can do both. But it requires building a telescope as big as 300 kilometers in diameter to reach the same resolution as a flyby with an array of cameras that are separated by a few meters.
Yes.
Yeah, I have two questions. First is...
Okay, just briefly, everybody's asking two questions, so if you can keep them brief.
Okay. What kind of laser can you have on board a 1 gram spacecraft that have enough power and focus and send us...
Right, so the question is about the laser. You can imagine having I mean, the laser pointer that I was using is a milliwatt scale, but you can put a watt laser on such a thing. And in terms of power, there is definitely enough photons there to reach the Earth. The issue that you're asking is, how wide is the beam? And at the diffraction limit, if you imagine, let's say, a meter, if you use, for example, a focusing device or a focusing structure, which is 1 meter in size, and the wavelength is roughly a micron, then 1 meter over a then 1 micron over a meter is 10 to the minus 6. So you get roughly a fifth of an arc second in terms of the angular opening of this laser beam, and it covers across a distance of 4 light years. The spot of that laser would be bigger than the Earth. It would be actually bigger than the Earth-Sun distance. So obviously, if you point it at the Sun, it will reach the Earth, and then you have to do a calculation of whether you, with a kilometer square receiver, you can get enough photons, enough bits to convey the information, and the answer is yes. We went through that exercise. So I can go with you over the details, but in principle, it's doable. So there is no showstopper. In everything that I described, there is nothing that from fundamental physics you can say it's impossible. And that's the reason we came out with the announcement. I mean, one of the challenges was, is there a showstopper? Is there something that you can say violates energy conservation, anything we know about physics that would make it impossible? And the answer is no.
We'll take one more question, excuse me. So, is that one? No speeches?
Well, the speech part is hard. Please, I'll say it's good for drawing requesters, but actually the question is, Frank Drake gives my class this summer kind of an armchair introduction to a lot of this. And one of the points he made is that, I think it's at Lawrence Livermore, they're attempting to focus lasers for fusion.
Right.
And of course, he couldn't say much about it, but it's something that's very active right now and very difficult. Are you working with these people?
Well, so this is called the National Ignition Facility, NIF, and in fact they are collaborating with academia. A fraction of the resources are allocated for scientific projects. There is some classified work, but they are also interested in collaborations. And their technology is very different because they have a very short pulse of laser, much higher power, and very different method of producing the light. And so the technology that they're using is not applicable in this case. It's a very short pulse of light, very high power, much less energy than we need. We need 10 terajoules, they have kilojoules.
So I think let's thank Avi again.